Yeah, I told you about how wear is measured. So basically volume, where volume is given as in the form of proportionality, so load sliding distance divided by the hardness, and then after this we find out the wear coefficient. So wear coefficient is given as this equation, and wear coefficient is a non-dimensional number because you can do the dimension here and it is non-dimensional. But this involves hardness which is not always available, so we for a practical purpose we make specific wear rate, which is K divided by H, which is simply given as the volume of material removed, the load and the sliding distance. So that gives the specific wear rate or SWR. So in this definition we assume that we have the wearing material is always in contact with the counterface. So if this is the pin which is wearing out, let's say I've got aluminum and this is steel. So, and since this surface is moving by rotation or by linear motion, this aluminum surface is always in contact and it is always wearing out. Okay, but for example, if I do the other way, let's say I want to, let's say this is aluminum which will wear out and this is steel. So when aluminum is sliding on steel, obviously aluminum will wear out and steel will not wear out, okay, because it is much harder. So that means if I want to know the wear rate of aluminum, so if you look at the top view, let's say we have pin on this machine, and in the top view this is the steel pin in contact with the aluminum. So this pin is moving like this. So at this point every cycle only once the steel pin is crossing. So once it crosses here, again it goes back and again comes back. So the situations are different. Here I am trying to find out the wear rate of this aluminum pin or whatever material it is, but this is wearing out every moment. Every moment it is wearing out, whereas in this case when I have got the wearing material is this disc and pin is the harder material, then at every moment it is not wearing out this point, if I think about this point. Okay, so in this kind of situation sometimes people use number of cycles rather than the specific wear rate. Okay, so how many cycles it has crossed this point, so that is more important. In this case we can simply say wear sliding distance. It can be meter or sometimes kilometers. In this case that information may not mean the exact thing that we want, so we will use number of cycles in this case. This also happens in the case of, for example, coating. So if I am studying a coating, and often we study many different types of coatings, polymeric coatings, diamond-like carbon, hard coatings and so on. So let's say this is a coating and I'm trying to study the coating. So often for this kind of situation the good thing is you can use the ball as a counter surface. Okay, so this is the ball. You can use a bearing ball or some kind of hard ball. Ceramic balls are also used. So again the contact is only a point contact, very small, and this is rotating. So every cycle it is crossing here once, every cycle it is crossing here once. So if I want to know the life of this coating, then it is better to report it as number of cycles, because distance may not mean much here in this case. So sometimes we plot curves like this one. So here I will plot number of cycles of rotation, and here I will plot let's say my coating DLC1, and this maybe I produced another DLC at different situation, DLC2. So here I will give a, let's say, bar chart DLC1, and let's say DLC2 is better in terms of number of cycles. So this is the way I would present. So we should know that specific wear rate is fine if we are in this kind of situation, but in other situations it may not be same. So often we have to adjust our methods and our presentation to suit the kind of work we are doing. So here we have got this wear rate as a function of the load, and leaded brass pin against hard statellite ring. So here as I said, there is a big change in the wear rate. It goes from 10 to the power minus 5 to 10 to the power minus 4 in this unit, and to 10 to the power minus 2. So this is a change, is almost orders of magnitude. So this is, we call it as a transition. So there is a transition here at this point, and this transition is known as from mild wear to severe wear. So this we call it mild wear to severe wear. So this is important for us to understand that this difference, because any kind of materials you are using in the mild wear, it is fine, you can use it, but you cannot use in the severe wear, because this is a failure. This is an accelerated failure, and so beyond this transition the material will fail. So whenever you are designing a bearing surface, you must design within this level, so that the load is here. So so that's why we need this kind of data, so that we can design and select the material very suitably, so that the load is within the mild wear regime. It should never be in the severe wear regime, because this is almost like a failure. So mild wear results in extremely smooth surfaces, often smoother than the original. So as I said last time, very fine polishing is a kind of mild wear situation, where the wear is taking place slowly. Of course, in the polishing we intentionally want wear to take place, so we might apply high load. We will increase the load so that wear takes place and my material gets polished. So it will produce a smooth surface, and debris particles will be extremely small, in the range of 100 nanometer, this kind of size of the debris particles. And if you are measuring the electrical contact, as I said, by electrical contact also you can find out the wear situation. So electrical contact will be conduction will be very less, that means the resistance will be high. So when the resistance is high, you assume or you understand that the metal to metal contact is less, and therefore wear will not take place so much. Okay, so that's why you see this drastically goes down and then goes like this. So electrical contact resistance measurement is another way to find out whether my bearing is going to fail or not. So this is a device you can apply. In the severe wear in this regime results in rough and deeply torn surfaces. So these two surfaces will be very rough and deeply torn. A lot of materials will be removed. So much rougher than the original material. Large metallic wear debris will come out, which the size will be in the range of 0.01 millimeter. And low contact resistance, that means high thermal conduction, electrical conduction. So which indicates that lot of metal to metal contact is happening at the contact point. So these two are very often used, these two terminologies, mild wear and the severe wear. Now so as I said, two factors, the load is there, and another factor is speed, relative speed, which is also important. So we must control the load and the speed to keep the wear regime in the mild wear regime as lower as possible. Okay. Here this part is far better. So if the wear rate or wear coefficient, I think this is a different unit. If I'm talking about specific wear rate, and specific wear rate is in the range of 10 to the power minus 6, then this is quite a very good situation. As we go to 10 to the power minus 5, it is large wear taking place, and beyond 10 to the power minus 4 it is not acceptable. It's very, very high. So let us look at the data here. So typical values of dimensionless wear coefficient in dry sliding. So this is wear coefficient, which is non-dimensional number. Materials were slid against tool steel in unlubricated pin on disc test in air. The coefficient of friction varied from 0.18 to 0.8. So between friction and wear, one important thing we find is that friction doesn't vary much. It is varying from 0.18 to 0.8. Okay, but wear is varying too much. Here you can see orders of magnitude. It is minus 3, it is minus 5, and it is minus 7 and minus 6. So several orders of magnitude changing in the wear rate for a very small change in mu. So this is very important to understand that, because often in many of the theoretical modeling, when people are doing and they need value of mu, and many times people just take some values, 0.3 or 0.5 0.35 or sometimes 0.25, but these two values are very, very small in terms of coefficient of friction, small changes, but in terms of wear it can have a very big change. And also if you calculate the forces required or energy required will be also very different, very wide difference. Okay, so that is very important for us to understand that small change in friction can make a big change in the wear rate and in the energy requirement, and also it can also lead to transition from, let's say, mild wear to severe wear. So this kind of also, so that is very important to understand. Another thing we can understand from here is we have got mild steel on mild steel. So this is a data for mild steel against mild steel, and we see that the wear rate is very, very high, 10 to the power minus 3, which is not acceptable for any application. So if you are using bearing material, if you have a shaft inside a bearing material, okay, so this is the shaft which is going to rotate, and bearing there is some load obviously. So this, if both are mild steel, they are not good, they should not be used. Okay, so this is another design rule, that we should not use mild steel on mild steel. Even with lubrication we should not use, and later we will talk about lubrication, how the lubrication actually happens, and why materials are so important even if you are using lubricant. So this is very important. And other data are against the tool steel. So you can see that with brass 10 to the power minus 4, PTFE 10 to the power minus 5, even though PTFE is not a very good wear resistant material, but 10 to the power minus 5. And then we see very good against polythene or polyethylene. This is PE. 10 to the power minus 7 is really a good value. And with PMMA also 10 to the power minus 6. So if I want to select materials here, I will simply compare this K value, and I can find out that okay, polyethylene is better, or after that I could use stainless steel or copper beryllium. These are also good. Okay, so this is a good way for us to compare different materials for our design purpose. Obviously we should also find out what was the mu. We should not neglect mu. We should not select materials just based on the wear rate. And here, as I've written here, there is no simple correlation between friction and wear, although it is generally true that high friction will lead to wear. Okay, so I had given you example of PTFE, that PTFE gives very low coefficient of friction, but wear rate is not very low, it is in the medium range or high range. Okay, so this is just one example. There are many such kind of situations where low friction doesn't necessarily mean low wear. The wear can be high. Another thing to understand is prediction or modeling wear by any analytical or computer simulation method is extremely challenging. Okay, now we have seen how friction and wear both depends on so many parameters, not just the two materials, but so many parameters: load, relative speed, temperature, environment, gaseous environment, liquid environment. So these are the main ones. There are many other parameters. System vibration. So because of this reason, modeling or predicting wear is extremely challenging. So perhaps you can only do that sort of comparing between two when all other parameters are same. Otherwise it is not possible. So numerical values of K is always much lower than unity. Another important thing, it is much lower than unity. So wear rate will always be lower than unity. The range of mu was between 0.18 to 0.8, but range of K was by orders of magnitude. We have also learned that a combination of similar materials gives very high wear coefficient. So dissimilar materials show much lower wear coefficient. And as I said, there is no simple correlation between friction and wear.
Excuse me.
Yeah.
Sir, I have a question. Sir, for designing in mild wear region,
Yeah.
sir, here load is external load, sir.
Yeah.
You are talking about external.
Yeah. This is a,
Sir, here load magnitude. Sir, here load magnitude is very low, sir, less than 10 Newton.
yeah.
But in our practical situation, this load are very much,
Very high.
the
Yes.
order
Yeah.
of thousand, 10,000s.
Yeah. It is good point.
Like in bearing, etc. So,
Yeah.
sir, there in where it is very high, but still wearing not failure.
Right. So actually, ideally we should present as in that form of pressure. So because this is experimental data, when you do the experiments you might be using a ball or a pin, and often the diameter is very small, so even though the load may be not much, but the pressure can be high. For example, this is point contact, pressure can be high. But yes, I fully agree with you that in the industry the load, or rather we should say pressure will be very high. Okay, but still our equipments function, and that function because um, there are many things. Okay, here we have not thought about using any solid or liquid lubrication. So this is leaded brass. Of course leaded brass has got some better wear rate, and but still wear rate will be very high. Okay, so for example wear rate is high for here, brass 10 power minus 4. So if we are going to use it for industrial application, we must use solid or liquid lubrication. Okay, otherwise it cannot, you cannot use them. And this is the one problem with metals. All metals have got generally high coefficient of friction, and therefore we cannot use metals without some form of lubrication. But if it was, for example, a polymer, there are some polymers which can be used at high load or high pressure without much problem of lubrication, because the polymer itself is self lubricating. But with metals we cannot use, with ceramics also we cannot use unless there is some sort of lubrication. So yes, it is correct that machines cannot run, generally machines run at higher load and higher pressure, but there we have to use some sort of lubrication.
So, sir, can we within the second or within the minute? Uh,
Sorry, the voice is breaking, so yeah, can you repeat it again?
Sir, if lubrication is not there in a thing,
Yeah.
then within the second or within the minute, machine gets failed because of high load.
Yeah, so if the lubrication is not there, then we have a lot of limitation of how much load we can use. So if it is within the mild wear regime, we can use it. But if it is severe wear regime, we cannot use it because this is a failure. So that is the limitation, and that's the reason why we have to understand how materials fail due to tribological failures like wear. So lubrication is a solution that we apply to solve the problem of tribology. Lubrication is one of the solution. There are other solutions like proper material selection, proper coatings, and so on. Is that okay? Any more question?
No, sir.
No, okay. Next we will look at this as we have seen that there is a transition, so how to present those data. So here pressure has been presented in the form of normalized pressure. Normalized pressure is defined as the actual pressure and divided by the hardness. So if we do this ratio, then this is dimensionless, and then normalized velocity, this is given as here, the actual speed or velocity divided by this k is the thermal diffusivity the nominal contact area. Nominal contact area is that we just calculate what is the contact area. Okay, actual contact area may be different, but nominal is just from here to here. Okay, like this, divided with pi. So this again gives a non-dimensional number. If you look at the dimensions of thermal diffusivity and the sliding speed, so you get a non-dimensional number. So basically, by making it non-dimensional, we can plot the data in a much better way. And there is another which is wear, which is given in this form. So wear volume divided by the nominal pressure, which is given as wear coefficient multiplied by the pressure. Okay, where this W is actually wear volume divided by the sliding distance. So again, this term the non-dimensional wear rate, is calculated this way. So now we can plot for any kind of material, and this is specific to one material. So it can be, for example, a certain type of steel. So for example, these are iso wear lines. So that means along this line the non-dimensional wear rate is constant. So you can see that for each wear rate, as we increase the normalized velocity and normalized pressure, the wear rate will change. Initially it doesn't change much, but after some time it may come down and go up. Similarly, in this case, comes down and goes up. And this whole map can be divided into at least 3 big regions. So if you consider this as one boundary, PQ, so here mechanical wear process, so this is the and this is the going right side of PQ. And as we increase the velocity, the wear regime can change into thermal wear process, melt wear, and above here it is scissor. So scissor is complete failure of the interface. So that means we should never go in this region. Whether at a fixed velocity, if we increase the pressure, so this is the limit. So we should be much below the limit. Okay. Similarly, at a fixed pressure, we should not go beyond this one. We should not go here either, because here there is a big change in the wear rate, and also this part. As well as melt wear also is a failure situation. Thermal wear also leads to failure. Okay. Here there is one thing that wear rate, the non-dimensional wear rate, starts going down and then it again goes up. So that means if we draw a line here, so we may say that for a fixed this pressure, same wear rate at 2 different speeds, which sounds a little bit paradoxical, because for the same speed, how can there be 2 wear rates? Okay, same wear rate. So this wear rate and this wear rates are same because this is on this line, but speeds are different. And this happens because at this speed some other actions may take place because of thermal actions. So other actions, for example, oxides can form on the surface. So oxide formation may take place, and as well as some plastic deformation may take place. So there is a thermal involved here, thermal action. So because of these reasons, sometimes the wear may be same, but actually the mechanisms are different. Okay, so that we have to understand that wear is not just a reflection of two materials wearing out, but it also a reflection of the mechanism that is taking place at the interface. There are other ways also to show these kind of maps. For example, you can show by ratio of interfacial shear strength. Divided by the shear strength of the softer material. This ratio and some other parameter, it could be a roughness parameter. So sometimes people also make the maps like this, and they say, for example, here you have elastic, here you have a plastic, and at some point you have got fatigue. So this kind of mechanical processes can also be plotted as in the form of map. So those kind of maps are also available for as a design guide, so that we can understand that we cannot go beyond this roughness and we cannot go beyond this shear stress, otherwise the interaction will be more plastic and fatigue failure. We want to stay in the elastic region. Okay, so these we have so far discussed about defining the wear and also talking about the important features of wear. What is important for us to understand, because in the industrial practice when the wear takes place, often people may not understand the mechanism or how it is taking place, so the solution will be very difficult if we do not understand the mechanisms. So there are more details about the wear mechanism, and here we have got major types of wear mechanisms. So we will discuss individual mechanisms, how it takes place. So the very first one is abrasive wear, and you must have learnt about something about abrasive wear, sometimes also called abrasion. So hard asperity acting with high stress involves fracture and plastic deformation of the wearing material. Relative hardness is important. So when there are big difference in the hardness between the wearing material and the material which is harder, okay, we will find this abrasive wear takes place. And for abrasive wear resistance, so abrasive wear resistance is basically means this is a number. Okay, so here what we do is we find out the wear of the material, whichever material we are talking about, and we divide it by the wear of wear volume of, for example, a standard material. Standard material could be mild steel, for example, because mild steel is very easily available and we can compare. So this ratio is known as the relative wear resistance. So always you have to look at relative to what. So we must be sure about this. So if copper has got this value of 11, that means copper is 11 times more wear resistant than the standard material, which could be the mild steel. And as we go higher and higher here, titanium is much better, molybdenum is much better. So as we increase the hardness, the wear resistance has gone up. So this is a very standard Archard's wear model, which says that the wear volume is proportional to the hardness. Wear volume is proportional to the hardness. So this is applicable. In these cases, you see these are the pure materials, pure metals, but normally we do not use pure metals for our engineering applications, often we use different alloys. So for example, A, carbon 0.48, carbon 0.83. As we are increasing the percentage of carbon, the wear resistance is going up, and with very high carbon percentage and some amount of chromium, here D is very high wear resistant material, and hardness also increases. So all these kind of situation, we can see that the Archard's wear law is very applicable. So we can say that Archard's wear law is applicable to abrasive wear. Okay, it may not be applicable to all other kinds of modes of wear. So we can see that this difference is there. In abrasive wear, we also have important thing. For example, one is called three-body wear, and another is called two-body. So two-body wear is very simple when there are two surfaces and one is harder and this is softer. So in this case, the asperity of the harder surface will wear out the softer surface. But three-body wear will take place when you have got two surfaces which, let's say, both are hard materials, like normal bearings are made of hard steels. So bearing steel, and let's say this is also bearing steel. But wear can still take place by three-body wear if this place, which is the interface, gets contaminated by some particles, and this can be a silica particle, also quartz, silica or quartz. So if contamination takes place here because of these dust particles, so they come from basically dust particle, then the wear will take place between these two materials. The bearing steel, both steel will start wearing out, and so therefore here it is basically the difference in the hardness. So for example, silica and quartz has got hardness of 7.5 to 12 gigapascal, whereas let's say if it was martensitic steel, which has got high very high hardness, so it is only 7 to 8 gigapascal. So in all situations, the dust particles like silica and quartz will actually wear out the surfaces. So it is so important that we should protect this interface. There are other kinds of particles as well which are also abrasive in nature. For example, boron carbide, and diamond is very hard material. Silicon carbide is also a hard material. Another hard material is called garnet. Which is a compound of some silicate. Okay. So these are all very hard materials. So for example, diamond has got hardness in the range of 60 to 100 gigapascal, and boron carbide 27 to 37 gigapascal. For example, garnet is 6 to 10. So these kind of particles will wear out the surfaces, but most common is By far the most common is silica and quartz, which comes from the dust or sand. So this is important to understand whether your wear process is abrasive in nature or some other, and whether it is a 3-body or it is a 2-body. Okay, so if it is 3-body, then your solution approach will be different. So for example, all the bearings, for example rolling element bearings, they are all sealed from any dust particle contamination. So it is sealed by a rubber, okay, or other kinds of elastomer, so that no dust particle can go in. The IC engines are all sealed from all sides, okay, to protect the wearing surfaces against this dust particles which comes out. So all tribological system must have this protection against 3-body wear. Okay, 2-body wear is something that we have to design properly, but 3-body wear is mainly because of the dust particles. But 3-body wear can also take place if I've got 2 materials, but at some point, because of whatever reason, some comes out, some material comes out, and it stays in this interface. So this also can become 3-body wear. So it is important to identify the mode of wear that is taking place before we can find a proper solution. Another thing is about the lubricating oil that you use will invariably contain some wear debris. No matter how good you have your lubrication situation, some wear debris particles will be always there. So for example, in IC engine, where we have got extremely good situation, it is fully protected and fully lubricated, but IC engine lubricants also contain wear debris. So how can we work with this? What is the solution? What could be the solution for protecting our IC engine? You know what kind of solution is used?
Sir, continuously departing and
Continuously uh,
sir, moving the lubricating oil in and out.
okay, but
Why?
the wear debris will go again in and out in the same way, right?
And we use a strainer for it.
Right, yeah. Filtration is very, very important. So we do the filtering in every cycle. So every time oil goes back to the engine, engine parts, we have to do the filtering. So this is a very, very important. So as you can see, in different tribological systems, we apply different solution, but these are the basics. We should understand why we have to do that. For example, if we do not do the filtering, okay, our engines will wear out very fast. So between the piston and the cylinder, the severe wear will take place here. Okay, as well as crankshaft and the cam, all kinds of wear will take place here. So filtering is very, very important, and just filtering also may not be sufficient. So at some interval of time we must go for oil change. So oil change is also the same thing, because the lubricating oil has now contains so much of wear debris that the filtering is not possible. It is very, very dirty. Not only wear debris, but there are also some thermal products, some degradation of the oil molecules, and therefore the oil actually changes its color from very golden color to very blackish color. A very new engine oil will look, well, I'm talking about for the car, but for some other colors are also used, but for automotive car here in India we keep the color as golden, and this will become like black. I think for motorbikes the oil is reddish in color, is red color, but again it will turn into black. So that's why we need to do the oil change. So abrasive wear is very, very common in industry, and almost 50% of tribological systems have abrasive wear, or if there is a failure because of tribological issue, and the 50% of cases it is the abrasive wear. But now we have understood that abrasive wear is not just because of the bad material selection, but also three body wear can also take place because of the dust. Normally, if abrasive wear takes place, you can see this kind of scratches on the surface. So this is a very typical thing. So if you see this kind of long scratches on the counterface on one of the surface which is wearing out, you can understand that this is abrasive wear. Okay? And so that's why it is also known as sometimes scratching, or when these scratches are much deeper, then we call it gouging. Okay? These are deeper scratches. So depends on the severity of the contact, and you can get these two situations. Okay, so the very first solution for any kind of tribological system is to select a material which is harder. So if I select this material, then I am much safer than this material, because basically the wear rate is wear resistance has increased, and that's why many of the solutions will be focused on keeping the surfaces hard. But even with the lubrication, so for example, bearing steels are very, very hard materials. So even though in the bearing we know we are going to use oil as a lubricant, or we can design as a rolling element bearing, but still the material is kept very, very high, so that any possibility of failure will not happen. Next is adhesive wear. Adhesive wear, just like abrasive wear, adhesive wear is also quite common, mainly result of adhesion between the interacting surface. So this happens when the asperities, for example, this is solid 1 asperity, and this is solid 2 asperities. So when these two asperities come in contact, so this is the interface, this is a place where they have come in contact, and if there is adhesion, okay, so adhesion can be high for similar material, right? We have talked about before, similar, let's say metals, let's say mild steel on mild steel, or stainless steel on stainless steel. So adhesion will take place here. Then what will happen is, because we are applying some motion or shear force, the failure will happen not at this point, or disconnection will happen not here, but rather at some other points. So path 2 is the shearing path. Although we can think that the shearing should happen here, because first of all the cross-sectional area is small compared to any other point, and another, this interface is full of defects. This is not one single material, there is a lot of defects. So therefore any kind of sliding should happen here, not another place. But since these 2 points are extremely adhering to each other, and also if they are not, this surface makes certain angle with the sliding motion, in those kind of situation the shearing path will be some other point here. So therefore this material has been removed now. So this material can be removed because of the shearing action. After this removal, this piece, which is the wear particle, might be attached to let's say the harder surface, or it may get removed out as wear debris. So depending upon the situation, depending upon the load, temperature, sliding speed, this wear debris can be very big. So it can come out as a big chunk of material. So the two types of words are used in industry. One is called galling, another is called scuffing. Scuffing is just the beginning of adhesive wear. So in the beginning, when adhesive wear has just started, we call it scuffing, but when it is much more severe, we call it galling. Both are not required, so we have to avoid this kind of adhesive wear, because adhesive wear will really lead to failure. So adhesive wear will happen not just because we have selected the bad material, but also because of lubricant failure. So lubricant failure because of its chemistry, for example, and also because of temperature rise. So in both situations, this adhesive wear or scuffing or galling can take place. So for example, here the image it shows on these threads, this galling has taken place. That means very deep deformation because of adhesion. They got stuck together. Okay, and you will see this kind of large chunks, not just this, very big chunks of materials will come out of the surface. So this shows the SEM picture, or scanning electron microscope picture. SEM image of this worn out surface. So as I said, when there are similar materials, when there is a lubricant failure, the adhesive wear will take place. So a very simple analysis has been done here. So for a sliding distance of 2A, so let's say this is the 2A, sliding distance from here to here. The wear volume, the material that has been removed is, let's say we model is in a simple way, make it hemispherical. Okay. Finding out the volume of this will be quite challenging, so we make it assume that this is hemispherical. So we can say that the volume, wear volume is 2 over 3 pi a q. Okay, so this is the volume of this hemispherical particle that comes out. So wear volume per unit sliding distance will be this divided by 2a, and that gives us 1 over 3 pi a square. We already know that the applied normal load, the total load, or whether we can also work in the local load just on one single asperity. But since we have got many asperities and we are going to sum them together, we can say that load is hardness multiplied by pi a square. Pi a square is the contact area. Okay, So wear volume per unit sliding distance is this one, 1 over 3 pi a square, and a square has been changed by this one, load divided by h, and this is summation of all the asperities. Now if you convert this into wear coefficient that we talked about, k, then it gives a fixed value of wear coefficient of 1 over 3. Okay, but in real practice, of course, we know that wear coefficient is not fixed, and perhaps it is much less than this one. So the reason is that not all asperity contacts will be wearing out at one point. So for example, if these asperities are wearing out, maybe the other asperity is not wearing out. Okay, so therefore the actual wear coefficient is much smaller than this, but still the wear coefficient is high, in a very high range, because adhesive wear is extremely damaging, and this is a complete failure of the material. So why I showed this scanning electron microscope image is because for any kind of wear event, looking at the surface is very, very important. Only by looking at the surface you can understand what was going on at the surface. So for example, if adhesive wear is taking place, you will see big chunks of material coming out. So you might have some holes here, or some material attached to this one. Okay, and also sometimes you might see the wear debris is in the form of some rolled particles. Okay, and this rolling happens because we are sliding here. Two surfaces are sliding against each other, and these loose particles are there. So these loose particles will roll back and forth because of some reciprocation action if it is taking place, and that turns into this kind of rolled particles. So this rolled particle happened because of the action, not necessarily just the removal process. The removal process might be just the chunk of material which got rolled into like this. It often happens in the case of polymers and polymer composites, that we see this kind of rolled wear debris. So this is also a adhesive wear, but the wear debris has changed its form from very irregular type, irregular chunk, to this kind of cylindrical shape. Okay, so we will stop here.